Okay, everybody. Good morning. How you doing? So, welcome back. Today we have sessions 3 and 4. Session 3 is focusing mostly on axial loading, and session 4 will focus on stress and strain. I think some of you have already started looking at the assignments and doing some of the problems, but if not, it's perfectly fine. And I think that you might even find that, going through things after having a little time to digest what we did last session on normal loading, will be able to, or static equilibrium, will facilitate fast understanding. I just wanted to point out a couple things with both stress and strain, and also with the work we're doing with axial loading. So first, with axial loading, okay, you'll see that we're now thinking of bars as springs, okay? And that's to kind of make our lives a little bit easier. It can make our lives a lot easier when dealing with systems that have multiple bars in them, and you have multiple spring constants, and then we can simplify and think about these networks of springs in terms of springs in series and springs in parallel. But before we even get there, right, we have this kind of very basic idea that if I have a force and I'm looking at the associated displacement acting on an axial loaded or a normally loaded bar, right, we can come up with a relationship that's kind of, for now, independent of what's going on with stress and strain, right? We'll talk about stress and strain. We'll talk about more detailed methods of handling this normal loading. But right now, what we're essentially doing is saying, look, there's just some spring constant, and I know that F equals K delta, and so you can manipulate this simple equation multiple ways, right? You can look at what the K is, you can look at what the displacement is, right? And you can look at what the force is. And I think it's also important to note, that this is newtons. This is typically given here in terms of kilonewtons per millimeter, all right? But it's really newtons per, it's some force per length, better said, okay? And then this is often in some type of units of maybe millimeters, or we're thinking of micrometers. Okay? But really one of the key things that I want to point out here is that we don't want to forget what we learned in static equilibrium. Okay, so if I draw this bar, okay, I first think, okay, I've got external equilibrium here, so the reaction force at the top will just be equal to the force being applied at the bottom. That's fine. Here we go. This is the key thing, though, that I would like you to remember, that when you break this member at some location, okay, it could be here, it could be here, it could be here. Wherever you decide to take that break, if there are no other loads externally being applied to the system, and it's not like a distributed force, right? You're familiar with those from statics, right? That's being applied along it. If there's no reaction force, no constraint, nothing applied along it, then the force inside, that internal force, right, is just going to be exactly the same. Okay. Now you're like, okay, that's kind of silly. Whoops. That I'm making this point. Okay. Why am I making this point? Well, The reason is that this Fi is essentially, this Fi here, right, is essentially equivalent to this F, is essentially equivalent to this F here. Okay, so when you think about what is the displacement that you have inside a member, okay, or from a member, or from a member in a system, sometimes what it's really good to do is figure out what is the internal force in that member. And if that internal force in that member is constant along the entire length of that member, then you can simply abstract it as a spring, okay, and figure out what the displacement is of that member in the system, right? And that's kind of one of the things we'll get at in the homeworks. This is the way we've drawn this is a determinate system, okay? And those are the types of systems that you were primarily working with in statics, okay? So the above and these are, familiar from statics. What we will also introduce today is this idea of indeterminate systems, okay? And a determinate system essentially says the number of unknowns that you have, like if you're looking at forces or moments, is equal to the number of equations that you have. So typically with a determinate system, you have 3 equations, okay, for determinant. So 3 equations typically, okay? And these are essentially some of the forces in the x direction. This is 3 equations typical to our kind of 2.5D systems, okay? For this is for our 2.5. Okay, typically we're not going to probably sum in forces in the z direction, okay, for a 2.5D. And the third one is the sum of the moments, okay, is equal to 0. So these are typically the 3 equations that you have, and you hope that you have unknowns, 3 unknowns or less, okay, for a determinant system. So for a determinant system, we have 3 unknowns or less. And typically, and so if it's like a beam bending problem, okay, often we just ignore the axial one. So normally we think of the axial one as the x direction. So we just kind of ignore that. That's a toss out because it's just 0 in that direction. Okay, but in the y direction, we have shear force internally in the beam. We have and then we also have the balance of the moments, okay, for these determinate systems. In indeterminate systems, or with indeterminate systems, okay, we have more unknown variables, okay, which typically are forces and moments, then we have equations of equilibrium. Okay. And so if you have one more unknown than you have equations, okay, that's indeterminate system to degree 1. And we're going to talk about this a lot more throughout the class. Okay, but this is just to give kind of a basic overview, and it kind of aligns with what you'll be viewing in the video. So for this, what we have to do is we have to find another equation, okay? And to find another equation, we have to go beyond equilibrium essentially. Okay, we're still using equilibrium because that gives us some kind of our base equations, but we go beyond equilibrium. To include geometry, displacements, okay, and this is what we call geometric compatibility. Okay. And we can think about deformation as well. Okay. And so what you'll see even today in this new topic, what you'll see is that we take information from deformation, okay, near the end of session 3, and we use that to help us figure out what an unknown force is. Okay, and in particular, you'll get an opportunity to look at this system. Okay, where there's a force being applied at the middle, right? Just a couple of things. If there were no, so this is indeterminate, okay? Because we can't use a moment equation. It doesn't give us any information, okay? We don't really care about, like, okay, so if we do like this, x, y, and then we said z is coming out of the board. The only equation that we have for equilibrium here is really that we can use, sorry, I got distracted. We can think about the sum of the forces and the x, okay? There's no moment information. Right, so we can't really use this. And there's really no sigma Fy, okay, in this problem, right? What are the unknowns though here? What are the unknowns? Yes, Michael?
The reaction forces?
Right, we don't know the reaction forces at the walls, okay? So you sometimes, what I'll do is I'll write okay. I'll write maybe a reaction force RL because it's at the left side, okay? And you don't have to write it this way, right? But, and also we have an RR on that side, and of course we have the force here, right? So we have two unknowns. And we only have one equation of equilibrium. So we need to use something about deformation, okay? Or we're going to be using, right? The other, you guys have heard this before, I'm sure. This is Hooke's law. Okay, so we're going to use Hooke's law in conjunction with equilibrium to be able to solve this problem. Now, there are a couple ways to do it. What's that? Sorry, oh no, just ask the question. What's the question?
Wait, what's that symbol used?
Oh, this is delta.
Okay.
Yes, this is delta. All right, it's not the best looking delta, but delta is what we use for displacement or deformation.
Great.
Thanks for asking the question, Matt.
I'll ask it to you next time.
No, it's okay. It's okay. So it's a small enough, intimate, and not well. It's we have like a nice, small group here, right? It's like an intimate gathering, as opposed to the 100 and something people that we normally have in a lecture. We have kind of two options to handle this. So first, I mean, this is indeterminate to 1 degree, all right? So indeterminate to first degree, okay? Because we have 2 unknowns minus 1 equation, okay? And that would be, so that's 1, okay? I often like to think of, when you're thinking about how many degrees of indeterminacy you have, I think it's easier to think about how many constraints do I have to release in order to make this a determinate problem, okay? So usually if you're thinking about degrees of indeterminacy, it's sometimes easier to think about how many constraints need to be removed. Now, you have to be careful with this, okay? Because you still should be, so I'll just say careful. Because sometimes if you remove a constraint, like for a beam bending problem, okay, that constraint actually is a constraint on a force and a moment, right? So if you have a wall, right, with a cantilever beam, that's actually 2 constraints, force and moment, even though it's like, or it's constraining 2 parameters, okay, even though it's like 1 actual physical structure. Okay, but here, okay, because we have no moment, it's pretty simple to see that this is a determinate system. If I simply remove one of the walls. This is now a determinate system. Now, another thing that I want to point out that is subtle, and also keep in mind that these general kind of insights that we're talking about here, they apply to shafts when we have torsion, they apply to beams when we have moments and forces as well. This system, if I'm interested in the displacement, okay, let's call this displacement here delta 1 and delta 2, okay? And we'll say that this delta 1 and the delta 2, these delta 1 and delta 2 are respect to ground, okay? So, if we wanted to call this A, B, C, right? Delta 1 and delta 2 we're going to say are respect to ground. So, what do you all think? How would you describe delta 1? And if I say that this is a K1 and this is a K2, what is delta 1 equal to in this case? Yeah. Yes, Mike?
Equal to just K over force, or force over K. Force over K.
Force over K, right? So that's the applied force over K. 1, sorry. Okay? Yeah, so because that's the K1, they could have different Ks. Now, what is K2, or what is delta 2 equal to? Yes, Michael?
Would it just be 0? Just moving it?
Okay, so this is good. I'm glad you brought this up. Remember, these delta 1 and delta 2 are respect to ground. So now, rethink that. I'm not talking about the displacement of BC. I'm talking about what is delta 2 respect to ground.
Then it would also be force over K1.
Yeah, it's exactly the same, okay? If these are with respect to ground, okay? When you don't, this is when it's sometimes helpful to think about what are the internal forces in the structure, in the different members, right? The internal force in the AB region is just F, right? And that is constant across that member, and that is going to be the force and tension that's going to be pulling this thing apart, right? And that contributes to the delta 1. The internal force between B and C, and this is what I think, Michael, you're getting at, right? What's the internal force in BC? 0, right? Big fat 0, because if I do the cut there and I expose the left, right? Just to be clear here, right? In BC, right? I have 0, right? So I mean, I can draw these things, right? But FBCI is equal to 0, right? So there's no deformation, okay? And this is maybe where it's important to distinguish between deformation and displacement, okay? BC is in fact moving, right? It's being displaced delta 1, but its deformation is 0. It's just like I like to say. You'll probably hear me say it in the videos, and I say it in person, right? Whatever. I am a person, okay? But I'll say it's just along for the ride, okay? It's just going for the ride, okay? But obviously, in the indeterminate case, okay, the deformation is not 0. Right? This side, though, if I were looking at this displacement, right, this displacement here is 0. The displacement on this side is also 0, right? But the deformation is non-zero in both of these. And it's because there are reaction forces, right, which then support or cause deformation in these members. If I, going back to this, and again, you'll watch the videos so you get a more detailed. This is kind of giving you a little bit higher perspective, hopefully, and repeating myself a little bit, right? This in here, if I take this cut here, okay, and this is, this is C, this is B, this is A, right? If I'm looking at this F, B, C, we'll call I, right? This internal force is not equal to F, right? It's equal to RR. Okay, so, or it's actually equal to the minus RR, right? FBCI here is equal to minus RR, okay? And the internal force here is not equal to F, right? It's equal to RL, okay? So, again, what we're doing now is we're starting to combine what we talked about with static equilibrium the last time, and we're discussing how to now add deformation to be able to solve problems that we previously could not solve because we had more unknowns than we had equations of equilibrium. Okay? All right, so that's, you'll get a chance to play around and do some things. Actually, I should probably, well, I'll skip that. We'll just say another tricky set of problems, right, for session 3. Okay. Involves deformation with rotation. Okay. Now, it turns out that if you pretty much use the algebraic equations that I give you, you can solve the problems, okay? Or if you use Colab, you can solve the problems just by putting in the new spring constants, okay? But please take a few minutes to understand kind of what's going on, that we can use a small angle approximation for sine or tangent, okay? Some people are like, why didn't you use tangent? Well, sine works just fine too. And in the end, as you'll see, as these beams rotate, You could decide that you want to use the sine or you could use the tangent, right? But for a small angle approximation, right, sine of theta is about equal to theta, and tangent of theta is about equal to theta. So it comes out to be about the same, right? Now I may be speaking Greek here if you haven't watched the videos, right? But this is a little bit of a tricky bit, okay, that you'll get a chance to look at. For session 4, okay, really we're focusing mostly on the focus right now is on normal strain. Okay, we will definitely come back and hit shear strain hard, especially in the last couple weeks, I guess, of the class, last week probably of the class. But for now, our focus is primarily on normal strain and stress. Okay. So we'll come back to shear strain. Actually, well, it won't be that long. We'll come back to it when we discuss, let's say, shear stress and strain, when we do torsion. So actually, that will be pretty soon. But the actual, transformations and things, this will be probably the last week of the class. Okay. So try to, I guess, get a pretty good feel for what's happening with normal stress, normal strain. And we'll spend more, right now, we're kind of looking at averages, okay? You're looking at, and those averages can be extremely accurate, okay, when you have a bar, okay, and there's no additional load. But we will get into situations where we're looking at how we integrate, okay, over these types of systems, and if you have a distributed force or distributed load on it, the local strain could actually be varying, okay, or local stress could be varying, right? Okay, so that's, I think, about, let me just see if there's anything else I should talk about. Yeah, the convention, I guess I should probably talk about this. You'll see that we start from in 3D, all right, which is, you know, a nice way to start. Often we're looking at a 2D element, okay, for stress and strain. So yeah, I think we should talk about this just a second, okay? So we will draw a ton of boxes in this class, okay? And this is what we call an element. Okay? And this is maybe it's infinitesimally small part of a structure under consideration. Sometimes we think of this as a material element because it's just what is this chunk of material and what is it experiencing. We will typically, not always, have an up and a down coordinate. And so what you might see us do is write something like, this is y and this is x, okay, like that. Our convention that we are going to use in this class, okay, could initially be written out something like this. Whoops, what did I just do? Could be initially written out as sigma 1, 1, okay, sigma 2, 2, okay, like this, for normal stresses. Now, what are these subscripts representing? X is going to be called the one direction, okay, like the band. And this means that there's something happening in XX. This means, and 2 is the 2 direction. Okay, so 2, 2, so that's the Y. Sorry, what did I say? 2 is the Y direction. So something's happening in Y and Y. This, we'll go through this in the video, but the first subscript, okay, the first subscript, so if you have a sigma, we'll call it MN. The M is for the surface direction. Okay, and the second subscript is the direction the stress is acting. Okay, so what does this mean? This means that this right here is a one direction surface. Okay, this is a one surface. This is the X, there's an X surface. So if I draw, and if you go back to like your multivariable calculus or whatever, if you have this plane, right, and you draw an orthogonal vector coming out of that surface, okay, it's in that direction. And so this is a one surface. This is an X surface, okay, because it's coming out. And then this stress is acting in the one direction. Okay, so now we call it sigma 1, 1. This is a 2 surface, so this is a sigma 2, 2. What we don't typically write, if it has the same subscript numbers, we don't write 1, 1. We'll just write sigma 1. We'll just write sigma 2. Okay? Now, technically, this is a sigma minus 1 minus 1. Okay? This is actually a minus 1 direction. It's coming out the surfaces of minus 1 surface. And it's going in the minus X direction. So it's sigma minus 1 minus 1. Okay? But if we look at equilibrium here, and when I say equilibrium, what I'm saying is that this has some very small area. Okay, this is actually a three-dimensional element that we're only looking at in 2D. So if we said this had some delta A, all right, so if we said this had some delta A, okay, then we would have that sigma 1, 1 delta A, okay, minus sigma minus 1 delta A, right, would equal to 0. This is saying that we're summing the forces in the X direction. Similarly, we have a sigma minus 2 down here. Okay, that's a minus 2 to minus Y direction minus Y direction. But as you can see here, that sigma 1, 1 and sigma minus 1, they are the same. So you won't see us write sigma minus 1. You'll just see us write sigma 1, okay, for this side. And similarly, you'll only see sigma 2. On these, and I guess what I'll say is, when these are positive, that means that we have tension in that direction. When they're negative or the arrows are faced inward, that's compression. Okay, so we can say that sigma is if it's a positive, that's tension. If sigma is a negative, that's compression. And you're like, duh, I could have figured that out. All right, but it's important to point it out. Now, shear stresses are tricky. And we have a convention for them. We don't get together with them. We just have another convention. Okay? Here, what you'll see, okay, is the direction these arrows go. What is shear? All right, we'll try to get to that in the video that you watch, right? But shear is essentially a sliding action, okay? And you've probably thought about putting a liquid between two plates. Okay, maybe you haven't thought about it, but if you have a liquid between two plates, and when you do fluid mechanics or dynamics, right, you have these two plates and you slide them against each other, right, and they slip. Okay, your viscosity, right, of a liquid is determined by shear. Okay, that we think a lot about shear with viscosity. So this is slipping. This leads to the distortion of an element, right? These stresses act to pull the element, so they change its lateral dimensions. Okay, very, very small. But the shear actually rotates. It causes the element to change its shape. It becomes more like a rhombus. Okay. So here, what we do is there are some conventions, like if you're thinking about Cauchy stresses, for example, which is beyond, but it's not completely beyond because we talk about it in the notes a little bit. But you could, well, let me ask you all. If I use the same convention I use sigma, what would the subscripts be on this arrow here on the right? Yes.
Sigma 1, 2.
Okay, right. And why is that?
It's on the one It's on the one surface, but it's acting in the two directions.
Correct. Okay. So this is, we don't use sigma typically, but some conventions would. But we typically use a tau. Okay, so that's another Greek variable. So these are sigmas. We've introduced deltas, sigmas, and taus now. And we say this is a tau 1, 2. Okay. Or what we'll say is it's a tau xy. Okay, that's the other thing. So I should have probably said that earlier. Sometimes we don't do sigma 1, we say sigma x. Actually, that's what we'll often do in this class. And we'll say sigma y, right? But this is tau 1, 2. Okay, this one right here, it's on the 2 surface in the 1 direction, so this is tau 2, 1. Okay, and this one over here on the left side, okay, that would be a minus 1, minus 2. And this would be a tau minus 2, minus 1. Okay. Now, it turns out, okay, that for this element not to rotate, right, because we're doing statics, right? This is statics 2.0 essentially. We don't want this element to rotate or accelerate. Okay, so it needs to this all needs to be in equilibrium. Okay, so what you'll see is that tau 1, 2, and so we could think, okay, if I have the shear stress acting on this delta area, right, that causes a moment. Right, so if I sum all the moments, okay, in the z direction, right, because that'd be coming out of the board, that needs to be equal to 0. And so if you do this out, tau 1, 2 is going to be equal to tau 2, 1 is going to be equal to tau minus 1 minus 2 is equal to tau minus 2 minus 1. Okay. So all these shear stresses end up being the same. Right? And I guess I can go ahead and add to the list that this would be tau xy, okay, tau yx, okay, and so this introduces the conventions that we'll be using. Okay.
So all the taus are equivalent?
Yes, all the taus are equivalent.
So you only need to find one.
You only really need to have a tau xy. All right. Now, what will happen? This is 2.5D world. Okay. If you think about this as an element that's a cube, okay, in these cases, all right, now we've got a, here we have, we'll call this, we'll call this sigma x, we'll call this sigma y, okay, we'll call this sigma z, okay, and that's saying now that we have an x, y, z like this. And I'm just trying to pick a coordinate system where it's following the right-hand rule, right? So z, x cross y is going to be equal to z. Okay. So here, what you could see is that I have my shear stresses, okay, potentially acting like this on these surfaces. And yes, all those, so if this is an x face, right, and this is a y direction, so this is sigma xy, right? All those shear stresses are going to be the same, okay? But I could have, for example, a shear stress acting on this face, okay, which would be, that one would be a sigma, well, actually, you tell me, what is it? It's a sigma
YZ.
Good. Good, Carlos. Okay, that's a sigma yz. That sigma yz doesn't have to be equal to the sigma xy. Okay, and often it is not. All right, and then for equilibrium, again, right, in this direction, it's hard to draw these, right, but there's one there, there's one under there as well. Okay. Okay, good. So go ahead, go through the video, have some fun. We're here, I'm here to answer questions. And I think, we have 2 sessions this time. I think some of you already started. I don't know, everyone just absorb the information, right? Don't worry about the pace, but make sure you get it done before Monday, okay, when we meet again. All right, good, go for it.
Your class Monday?
Yes. Yeah, classes are Mondays through Thursdays.
Did you say that you weren't going to be here on Monday?
Oh, you have a very good memory, Matt. Okay, so you're right. I am just this Monday. I'm not going to be here. Okay, so so I won't be taking attendance, and what you'll be doing is having the opportunity to continue though. So. Session 5 will be available for you. Okay, so there'll still be something due Monday at 10:30, and there will still be something due Tuesday at 10:30. Okay, even though I won't be here. This room will be available. I'll be somewhat available on GroupMe, so if you have questions, right, we can go that route. Okay. Oh, and all right. So let's see. So team wise, all right. So let's see. I think Kayla's.
Yeah, the 4 of us.
Well, you can work the 4. That's right.
Yeah.
4 of you. So we're missing. Okay, we're missing. Well, I'll take it next. But yeah. Okay, then we're just missing a couple people. But yeah, the 4 of you are a team. That's right. Okay, good. Okay, Bowen. Good morning. Good morning. Mark. Good morning. George, what's up? Green, good morning. Tyler, good morning. Carlos. you all finding the slides now where I put the problems in it as well? Right, okay, so it makes it easier to know which problem you should do, okay, because it's not in the videos, I understand. In the later videos, it'll be a little more clear what the problems are, but in these earlier ones, this is a modification. Okay, just making sure. Because I know they're out of order. The problems are out of order a little bit. What's up? Did I say something funny?
No.
It's something else.
Okay, good. If you have suggestions for how we can add some appropriate humor to our content, just let me know.
Okay.
Like this way. So basically, flip this back.
Really, it's totally. Just do this. You
this will go, this one.
That's not gonna. Multiply the multiply the numerators as well. And that's an equal large. Yeah, that's right. So that should be like what you're next. Stuff here. Oh, you also have to do all the.
Oh, right, it's,
You might just give me your stuff over here.
there should be a little, it's on medium.
Yeah, that's what I thought too, but I can answer on you and stuff. This page is not very long. It should be on the order of 1,000. Should be on the order of 1,000. Did you multiply by 4 or 4,000? One or two. It's probably just. Yeah.
That's the answer.
Equation items.
That's the answer. That's the answer.
Should I? That explains these things. It's because, oh, you're off by 3 because since it's killing, you're, yeah, that's down to 6. So you're off, like, you're off by 3.
That's 2 or 3 times the interest rate. Well, okay, so, these are external loads. So, in this scenario, F2 is not necessarily compression or rotation, right? It's just that's the direction, right? So if we have, is that how it was? Yeah. Okay, so if we look at so what we're really doing here is looking at, okay, so when you say it's a minus, there's a minus inside of F2, but it's not, yeah, F2 is minus, is not negative, right? right? What we're talking about is the delta two, right? And what's happening with that delta t. So in this superposition problem, right, we're just looking at the contribution of this F2. We're just looking at the contribution of this F2 right here. So just without seeing all these algebraic expressions, if you put an F2 going this direction, which direction do you use? That end of the
Like this one?
This is just deformation, this is not a force.
Is this what we're
Right?
saying?
So this is a free, let's say I have, this is the one that is from the, this is the
I
bottom.
don't remember between the first and third link.
And I am applying a force
But
this
that's gonna have
direction,
the annotated slides and also say what questions.
alright? And this is a spring. I'm applying it this direction, which direction is this going to go? That way, right? I just went ahead and sometimes when you're doing these problems, you want to write the displacement in the same direction for all components, right? But like you just said, right, this force being applied that direction means that this point here is also going to go in that direction. So that's in a negative of the way we bridges. Okay, so that's why it ends up having a negative. But it also turns out that, well, when you do all the math now, right, that's a theory as well. But one way to think about this is now this is one member. Right? Well, remember how we just found that this member is along the ride, right? Because there's what's the force in this member? If for this, like when we broken it up, if the only two forces acting on this are from the wall and from this F2, what's the force in this member?
Which is, what, 1,000 times more directions it goes, right?
Or what's the internal force, not the direction, it's not always the internal force, just for this purple region.
Because that's probably what I did the first time. I was like, what is it?
Okay, well, if I take a slice and I expose the left side, right, so Jeff Hansen calls this the cover-up method. So now I take a slice and just put my hand over it. What's the internal force if I slice it? Is there any force acting on it?
Yeah, a lot of those zeros out with us.
There's no force actually acting on it, right? If I put a slice here, put my hand there, there's nothing acting on it yet, because I'm not using F3. We're only looking at contribution from F2, because we're doing superposition. So there's no internal force.
Yeah,
Alright? So that means that these two members are the ones that are experiencing the load, okay? And if I have this number and this number, that means the series will show. Okay, so we're looking for a equivalent, right? So this is the series. Okay, and then this F2 is being applied to it. And this is just along for the ride, because there's no internal force, right? But then, of course, there really is an actual problem, right? Because I have F1, F2, and F3. So we're summing everything else. Does that make sense? Right, we're breaking it down into its individual. Okay, thank you for asking.
Yeah, we were.
Do you have questions? Yeah.
There's displacement between like here, but it's not forming one. It's not going to form one.
Well, okay, it will, all right. Okay, now, is anyone, what number is this? Is anyone else working on number 4 right now? You are? Okay, let's talk about this, all right? Because this might, I understand it's on the video, right? But maybe we can talk about this problem a little bit. Okay. All right. Okay, so this is question number 4, I think, session number 3. All right. So there are three regions to this problem, right? Something like this. And you can correct me, but I think there's a force F3, there's a force F1, and there's a force F2, okay? These three forces are acting together at the same time, okay? But what we're going to attempt to do is to use the principle of superposition, okay? So we're going to pretend that this structure is experiencing these individual forces, and then we can add up the displacements from these individual contributions to come up with a final contribution, all right? And in this case, right, we're interested in, let's say, this delta at the end, all right? And so delta, right, can be thought of as a sum of contributions, okay, from deformations due to F1, F2, and F3. Okay? So what are we talking about here? Okay? We're talking about breaking it into a problem where this is equal to some deformation due to just F1 at the end, okay? Some deformation from so we're doing plus, okay, deformation from F2, that's going to be this force being applied here. And this is really poorly drawn. I wish I could just blame it completely on the tablet, but my handwriting, while legible, I think, is not the greatest looking. Okay, so, and then this one is got an F3. Unified. Okay, so let's talk about this. For delta 1, okay, what would you say the deformation is? This one is pretty simple, right? What is the deformation delta 1 in this case?
F1 over K.
Okay, so F1 over whatever the K is for this member, right? Just this member. Okay, so that's good. Okay, so delta 1 is, did I say this was K1? I can't even remember. Is that K1 or are they all the same K?
Yeah, that's K1.
K1, all right, so F1 over K1. I guess I can look at the actual problem. Okay, yep. All right, so now, remember we talked about what happens to members beyond where a force is applied? What is the internal force in member 2? What's the internal force in member 3? 0, right? It's just 0 because there's no, if I take a slice here, right? There's nothing on, like if I take a slice on this side, right? I just have this and I'm like, oh, there's an internal force, maybe, but there's really nothing over here, right? So this internal force, right, this is just 0. Right, and the same thing over here. Same thing in that region. Okay? So coming down to this one, what's the internal force in this member? Also 0, right? Because there's nothing on the end still. Okay? What's the internal force in this member? F2, and this member over here. It's going to be F2 as well, and the force in here will be F2 as well. Now, why do I know that? Well, I have in my mind that this is a spring, and this is a spring, and then they're in series with each other. Okay, so I would just say, I know from my experience that if I have springs in series with each other, they're all experiencing the same amount of force, but they have different displacements. Springs in parallel have the same displacement, but they have different forces inside of them. Okay, as if the spring constants are different, right? And that's the same thing, right? So if you think about a spring, right? Because and this is kind of maybe another fundamental concept that we should you should have, but if I break this, I have this pen that I'm pulling apart, and if I take a slice, the spring is no different than slicing. Remember we talked about this: slice here, slice wherever you want. But if there's no constraint or no reaction or no external load, right, on this system in between those two locations, the force has got to be the same throughout, along, okay, that region. Same thing with a spring, okay? These springs are in series with each other, so their force is the same throughout. Okay, so these are springs in series here, okay? So then I know how to create an equivalent spring constant for these two members. Now, before I even write down the equation, if I put two springs in series with each other, and let's just say they have the same spring constant, like a K1 and a K1, does the overall stiffness increase or decrease as I stack springs next to each other?
Decrease.
What?
Decrease.
Decrease, right? It's the idea of something becomes springier, right? That if someone tells you, oh, that feels springier, or wow, that cushion is cushier, right? I have increased the thickness, and now it feels softer. Okay? So as you increase the thickness, or as you stack springs in series with each other, the effective spring constant goes down. Okay, it becomes squishier in very technical terms. So if, though, I take springs and I put them in parallel with each other, right? So now I add a third leg to these tables, or I add a fourth leg to these tables, right? That's the same thing as putting more springs in parallel with each other. Does that structure become stiffer or squishier? It becomes stiffer, right? So that's what happens when you put springs or bars in series or in parallel with each other. Okay, so right, we can all begin to think of, oh, there are suspensions on cars, right? There are suspension bridges, right? And so as I use more members to support this load, it's going to become stiffer. Stiffer is not always better, okay? And that is not something we well, it's for multiple reasons, okay? It could be function requirement, but stiffer is not always better, okay? Because, okay, I will go on this digression because I got your attention. Everyone used a washing machine before? Maybe? Okay. Have you ever felt the hollow cylinder in the washing machine and pushed it? Does it move a lot? Why would they do that? Why in the world? This is something that has to not explode, right? And not rattle, right? Why would they make it so wishy-washy? Yes?
So it can absorb the force of the spin.
Okay, so it can absorb the force. But why would I make it stiffer, right? If I want, why would I not just say, put really stiff members and make sure that spinning cylinder does not move at all? Why would I not do that? Yes.
Because that would spin.
Or Ethan.
If it's stiffer, it's gonna be more force on it, and so over time it would break down, or just other parts would crack, and there'd be more stress.
Okay, yes, Michael.
If it isn't loaded evenly with the clothes, it's gonna push all of it to one side and it's just gonna keep banging on it.
Okay. So this is a frequency dependent system. All right. Do you remember this is a digression. What is this? This is a mass spring, and you're like, remember, or some of you probably, you're taking differential equations right now, right? If you haven't already taken it, right? Okay. What do you remember about this? You remember that there was an omega n, right, is equal to the square root of k over m, maybe? Okay.
Yeah.
Right? So, and then you remember also these systems, right, where you had the pulleys, right, and you figured out, okay, there's like a natural harmonic frequency, right? At this thing kind of explodes. It just starts like with a really little bit of input and it goes big. Same thing with your dishwasher or your washing machine. Okay, dishwasher, not so much. Okay, what happens? Yes, Mark, I'm glad you're getting it. You got it. All right, that's exciting. Okay, but anyway, I'm sure you're talking about something else. They're doing the problem, right? But what happens, right, is there is a resonance of your washing machine, and it's frequency dependent. Okay, so omega n, right, this is in radians per second, so if you multiply, there's a frequency, right, that's equal to 2 pi omega n, right? So as that thing starts spinning, it's really wishy-washy in there because you actually go through the resonance. Okay, so if that thing is actually spinning very slowly, it will access, right? So if you have a low k and high m, then that means omega n is low. The resonant frequency is low. If you have a very high k, then that means your resonant frequency is actually very high. And what happens if you look at the frequency response, it actually does this. If this is the magnitude, and this is the frequency, okay, and this is omega n, okay, it will peak if your spinning speed ends up being at the resonance. But what we do is, or what they do, is they purposely design the resonance to be very low, so it's very wishy-washy. And then they actually go through that resonance as it's starting up, and they operate out here. You see that? And then because this is a second order system, okay, it decays tremendously. So the amount of vibration that you have goes down exponentially. Okay, it goes down quite a bit as you increase. For every 10, you get every factor of 10, you're going to get 100. Okay, decrease. Right? It's pretty cool. So anyway, that is that's how this. That's why stiffness, okay, so we got on the digression, but this is why stiffness is not always better. Okay, stiff is not always better. One of the reasons, if you're doing vibration, which is completely not what we're doing in statics, all right, but it's just for your good to know file. All right, so anyway, back to this. If I put these two springs in series with each other, it becomes springier, right, and the KEQ, the K equivalent, right, is going to be K1, K2 over K1 plus K2. And, this is K1, and this is K2, right? And this member right here is just along for the ride, okay? Now, that's a spring, effective spring constant. Which direction is this displacement at the end going? Is it going to the left or the right? It's going to the left, right? So delta 2 is not going to be positive. Delta 2 is going to be negative because of the way we've drawn delta 2. Okay, so in this case, I would say that delta 2 is equal to minus F2, minus F2 over K equivalent. And then here for delta 3, right, this one we had to do all of them in series with each other, right? So it's probably easier to say that the K EQ2, we'll call it, right? That one is 1 over K1 plus 1 over K2 plus 1 over K3. And in this case, all three members are experiencing the same F3 force. Okay? So delta 3, right, is going to be equal to this F3, and it is positive, right? And it's going to be times 1 over K1 plus 1 over K2 plus 1 over K3, right? And the total displacement is a summation of all three, okay? But this problem kind of exhibits some interesting properties. One, we get to see how these members are just along for the ride again, okay? These two members in this problem, this member over here. Two, we get to see that if the force is in the opposite direction of a prescribed kind of displacement, then we need to add a negative sign, okay? And then three, this is a superposition problem. So we can put all these things together, okay? All right, good. So that, since multiple people are working on it, hopefully that helps a little bit. And I can go around and provide further clarification. Yes.
So to get the elongation, you pick D2 and subtract D.
Okay, so to get the elongation of the middle member, all right, we need to figure out what the internal force is. Okay. So now there's a question. What's the internal? How do I figure out what this deformation of the middle member is? Okay. So how do you figure out the deformation of the middle member? What do you guys think?
You isolate the middle beam.
Okay, so we isolate the middle beam, all right, and what are we isolating it to have?
Just F2 and F3.
Good, all right, so what he's talking about, all right, is the following. What we're saying is, remember, in order to figure out deformation of a member, we need to know what the internal force in that member is, or the force along that member is. Okay, so for that, let's do it this way. Okay, and we say, I need to know Fi, the internal force. Okay, and in this case, I've got an F1 here, all right, and I've actually got, if I copy this, I've got what we'll call RL. Okay. So the internal force right here, if the way I've defined RL at least, okay, the internal force is going to be Fi plus F1 minus RL is equal to 0. Now, so that means that Fi is equal to RL minus F1, like that, okay? So if I want to know just what the deformation, now, remember, this comes from this problem, where I had 3 members, and this is K2, that has a spring constant of K2. If I know the internal force, then we can calculate what we're going to call delta BC. All right, if this is B, this is C, this is D, this is A. All right, delta BC is just going to be this internal force divided by K2. All right. Yes.
So is RL equal to F3?
No. We have to do external equilibrium,
Oh,
right? So, yeah, I didn't quite do everything here, right? But I often do. That's not a problem, right? But yeah, so to figure out RL, right, we have to do F1, F2, F3, and we have RL. Okay, and I don't remember if RL is really to the right or the left, to be honest. I don't remember, okay? Okay, but maybe I did this a more complicated way than I had to. I think, Carlos, you said, let's just use F2 and F3, maybe. Did you say this at the beginning? Maybe you didn't. Maybe I'm thinking you did. All right, so who said it? Mark said it, right? The simpler way, right, to do this problem is to say that this internal force right? This internal force is going to be related to, I shouldn't draw it there, F2 and F3, okay? So now, if I do the summation here, okay, what we have is that I have Fi plus F2 minus F3 is equal to 0. So Fi is equal to F3 minus F2. Okay, so I don't even have to calculate out RL. And of course, that Fi is the same as the other Fi, right? And this again illustrates the point that these guys, this Fi and this Fi are the same, even though they're drawn in opposite directions. And the other thing to keep in mind is that Fi is positive. If Fi is positive, that means that this member is under tension. Okay, if Fi were to be negative, it'd be in compression. So, but I need that Fi in order to calculate my delta BC. Okay, good. I'm glad we had a chance to talk about this. It's starting to get a little more real, right? From what we did, I know, baby steps, right? It's going to get there. It gets, even the rotation problem is kind of nasty. Or not very nice. How are you doing? Good to see you, Hulu.
Yeah, I missed the train.
Okay, I gotta make sure I mic you here.
Yeah. Thank you.
So what do you mean by That's exactly right. So, if you watch the documents, he causes to have a so what he does, what he says is like, look, I'm gonna put my hand here, I'm just gonna cover up get the rest of the problem, right? And you can cover up the left side of the chart, you can cover the right side. So, stupid one is, okay?
All of them.
Good, good. Okay, Michael.
Yeah, really like 10 minutes there.
Okay.
I was kind of confused, but my answer was right, so I'm just gonna take it.
Well, no, yeah, that's one way to do it, but no, let's just discuss it.
I don't understand why this spring concept.
No, creo que eso es
Third,
I don't know, really missing that.
but why, so the internal force is the third member in F3, right?
Yeah.
So does that mean when it comes to deforming the second member, is it F3 or F
¿Por qué yo
or
puedo
is
más
it just still from the same force coming together?
That's right, so you, I think you just answered your question. So the F2, or third member is stretching, when it thinks about its deformation. All it cares about, in terms of its elongation, all it cares about is what is the force? What are the forces, or what's the internal force, right, on it? And as we just discussed, the F, like, if no matter what I change that third member to have a stringiness, it still transfers the same amount of force throughout. Right, so that second and middle member only cares about F3 acting on it. It doesn't care if it's, if member 3 has stretched this much or this much or this much. It doesn't care. So it doesn't care what the spring constant is.
That's because the internal force in the third member will be F3 no matter what the spring constant is.
That's right.
Okay.
That's right. Okay?
I'm on.
Good, good.
I remembered why I was confused.
Okay.
I asked them.
Okay. Yeah.
Because on this part, if you're taking it, like you're covering a bit, but you're still only considering.
Well, actually, this one, yeah, so this one, okay, yeah, so for E, yeah, so I could cover up, we agree that we could cover up here, right?
Mhm.
Okay, and then so the internal force would be still the R1. So if I then know that the internal force is R1, right, then I can also think about what the force here is. Okay, and in terms of, this is maybe not, yeah, so this internal force is R1, right, and so this is gonna be, this is a little, yeah, this R1 should be, but this is the internal, I think this is the internal, this is the internal.
These are in parallel, so just.
So
Just do
this
it for
is,
that,
this is,
and
yeah,
then
this
that,
is,
and that.
They're all parallel forces.
Parallel,
this R1 right here,
Parallel,
that
yeah.
is causing
you just add it,
the,
right?
Parallel?
Parallel?
I can pull it from here.
Yeah, like that makes sense, because he said it gets stringier with a.
that's right, so that's what I did initially, yes.
Alright, so it's just 4 times K.
Yeah, let me keep noting, this is a little bit, this is a little bit confusing because we have the F there as well,
Mhm.
right? So I can see how that can cause.
I think it's just moving.
Good, but this is still true. This is still true. Okay. Good.
I really hate that they use the same ways that they do resistance, because they're like completely opposite, they're literally opposite. Probably not, if you put more materials with it. So I just wonder if it's very cool. So parallel, we just add them.
Yeah, and if there are questions about springs and parallel and series, I do talk about it a little bit, but I also, there are videos on the website that have the derivation for why you add spring coefficients in parallel and why you have to add their inverses in series. Yes, George.
that's what I'm saying. So you have to. For series.
So you had to look like
Can I break it down? Love file.
Sí, vamos a ver.
right, so first.
No, I just.
Ya ha pasado, ya pasó una
Sorry,
semana.
it's 1/4 now.
Like I did here, right?
Yo no sé si la mañana.
It's one thing that this file makes us all do. We have to draw.
No,
And you can't just jump right to the variables. And then put another one
vato.
down. And then you're gonna do two.
Ayer hice carne en casa. A ver, estoy saliendo ahora todos los días. Pero tengo que hacer fuerza. Si no, mis músculos se van.
Okay, so what do we do here in this case? The first thing we do, we kind of start at the top. We create an equivalent spring, right? So there's two springs here, so then we create one equivalent spring here. So
entrenar
yeah,
por
you're
lo
gonna
menos
need some more stretch.
una cada semana.
Mi bíceps era de este tamaño.
That's fine. I used to go to the printers in the computer labs and take out, or they had a recycle, I didn't take it to the printers, but they had like a recyclable paper right next to it. Okay, that's good. And here's like,
De jiu-jitsu.
one spring.
Hay un club de jiu-jitsu.
No. Well, okay, so, yes, you're right. Okay, but why, so why is that? Because those are all acting. They're all
Aquí no creo que
acting.
es que
Yeah,
su box es
yeah,
más.
so go ahead, that's fine. That's right, you had it so four,
Yo hice
I'm
cuenta.
sorry.
Bueno, también se va.
About 2 years.
Pero es que ahí necesitaba que.
Oh, but this is.
That's right.
This is
Aquí no hay, es que siento que acá sí se van a pegar. Si hubieron clubs que se perdían mucho, yo creo que eso. No, ahora que lo menciono, tengo espaldas. Había
Well, you combine all three of these, and there are three springs in series.
¿Sería? De todos.
Right, or you could do,
Había clubs de
you
espaldas,
could do
están jugando ahí,
springs in
en el
series, right, and then put that in series with this, right?
Sería
But
bueno.
if you have three in series
Creo
with
que
each
te
other,
dejo.
the easiest thing to do is to do, 1 over k EQ for the whole system is gonna be equal to 1 over 4k1 plus 1 over 2k2 plus 1 over k1.
Yeah, it was.
Yeah, you can, then that would be 5 over k1.
That shouldn't be, this shouldn't be.
Oh, sorry,
What's
no,
wrong?
This is, I'm sorry, I did it wrong, This is 1 over k1. Yeah, 1 over k1. So now, yes, you can combine these, right?
Oh,
This is
try against the.
4k1.
I'm so confused.
Over 4, so it'd be
Wait, no,
5
I
over
thought
4k, 5 over 4k1. Plus 1 over
Yeah.
k.
No, because that.
That's 1 over k.
That should be that.
Okay, so now, F equals
Yeah.
k equivalent times delta, right?
Because that's the. Wait, no,
F
no,
equals
no,
k
you're wrong.
equivalent times delta.
Yeah,
Right, or
what is
F
that?
over
What did I
k
do?
equivalent is,
Oh, this should have been,
so
wait.
F times this,
This should have been.
Aún no hago ninguno,
I don't remember.
pero está fácil.
That's so.
Oh,
Acabo
so
de
now
verlo
we
y
just want the, so we just want the thing.
entonces exactamente igual.
It's
1 over this entire.
Más bien, cada vez que veo
Yes.
fácil, yo escribo al lado.
Okay.
That's actually one of the creations.
Yeah, that's right. Yeah. No, just let me know, Aaron, you know me, I didn't say.
That's like two.
Yeah. No
Do you remember the?
I make mistakes, so.
You literally ask them this question. Never like get the question wrong.
Yeah, here's the calculation. You
El
literally-
problema es,
Do you remember, we were talking about?
no sé por qué las primeras preguntas están
Yeah, no, that was. There's no way. Yeah, because I looked at the syllabus and we were doing that, and it's like, that's major. I think that was like, yes.
definitely not, I mean, we know that the R1 is not equal to the F,
Yeah.
right? But, you could just use, you could just deal with the slice, right, coming from the left and exposing the right, and then don't try to have a controversial what's coming out on the right side. Good.
This one is a middle.
I'm talking about that. Question itself. Wait, why does it give us the links? Why is that? Oh, that sucks. It hasn't been displacement. Because it's like, I mean, actually, I feel like it's something like would you get? That's like strings like this. So I think it's those plus some.
Displacement.
Okay, so I just uploaded on the website. There was a slight change here on, I guess it's slide 30 in session 3. It's just a slight thing when you're calculating out the delta B relative to A. The diagram was a little bit misleading. So,
Thank you, Kayla.
what there was before was the slice was coming from the other direction, and we know that we know that R1 is what the force is internally across this member. Okay, and so that's the force we want to use when we calculate how much it deforms. But it was a little confusing in terms of what was written on the right side here.
Parallel just did you get 2 different things for this? Like 2 verifications. I just used. Yeah, is that 2 things? Yeah, that's weird. It's not really something. This is a news. Yeah, it's in there. It's killing us. Okay, just in the room. Okay, because yeah, I don't even see that. I don't have to familiar here.
No, I said, I always think there's something like this, so like, I was like, alright, I reread the fucking instructions. Yeah.
Okay, so you can just use this. So you use the
this one it says there is rigid and no rotation. Right? This is a simple flat.
So the displacement for here uses this displacement, this one doesn't.
Yes. That's right for the first column.
So
But not for the next. For the next, if we ignore the, because we're ignoring the rotation.
For this example, but on the homework question.
Yeah, for the homework problem, there is rotation.
that is something complicated.
Yes. It does make it a lot more complicated. So I would watch the video to see how you do it, right?
I was looking at the video, didn't go over the problem.
No, that's. But in terms of how to do this and get the right answer, this is when I would use the fill out. Because the code is already in it. So all you do is just Alright, but you want to be able to do it both ways.
Yeah.
Okay. Yes. How's it going?
Exams. Are we allowed formula sheet?
Oh yeah, okay, yeah, you can announce that, yes.
We start doing
Yeah. Okay, so guys, there was a question about exam 1 and subsequent exams. Exam 1 is on the 13th, I believe? The 13th, okay? So, you will be able to bring a formula, or actually a note sheet. It's not even a formula. You can write anything you want, all right, on the formula sheet. 8.5 by 11 inch, or what is the other? What is it? A1. That's right. The A1 side. Whatever. I don't know. Whatever it is, right? You can write whatever you want on both sides of that sheet of paper, and that's what you bring in for the exam. It must be handwritten. Okay? So no copying and pasting. All right? Either digitally or physically. But if you want to handwrite it in OneNote or your other digital handwriting thing and print that, that's fine. It just needs to be handwritten.
What's about last time?
Okay? Yeah, that's the rule. But it's, and so it gives you a chance. So you could already start writing it now, right? If you're doing it and you have a digital digital thing that you're doing, you can start writing the equations down as you go if you want. Don't make it, but with digitally, don't make it microscopic. All right? Okay. Shouldn't need a microscope to be able to read your digital numbers.
Escribir la Biblia. And then you have to figure out the date. So we'll share or she'll take.
Okay, I believe the time has come. I think, so there was a guy from organic chemistry here yesterday, but I'm not, I think they're doing, I don't know, but today's a different day of the week, so I don't know if anyone's coming here, so if you wanna stay here and keep working, you probably can, because that person has not shown up. They said their session was at 12:30, I don't know, but you're welcome to stay here, but I'm gonna head out. If you have questions, group me.